We're going to look at the second half of Chapter 16's book problems, or at least a selection of them. And we're going to start off with number 27. Here's an example where I'm going to give you a mean and a standard deviation from a distribution, or in this case, two distributions, the x distribution and the y distribution. What that means is that we don't know all the values inside that x list. We don't know all the values inside the y list, but we do know the mean and the standard deviation from those data sets. And what we want to do is we want to do a number of things to either re-express this data, whether I'm going to be doing things like A, where I'm going to be multiplying by y, or here we're going to be multiplying and subtracting, or at the bottom here in the last three, we're really combining two different distributions together. I will say that A and B are different. This is rescaling and shifting. When you get down to C, D, and E, you do see some rescaling happening, but you have an x plus a y, or a y plus a y, or x minus y. The game changes when we get to C because you're combining different distributions. So take notice of when we get to that one. Okay, part A. In this example, you are looking at 0.8 times y. Well, I'm going to take the mean, 0.8 times 300, and essentially when I just multiply that together, I'm going to get the new mean of the distribution. So this is going to be 240, and then we're going to have the standard deviation, which is going to be exactly the same, because when we multiply, when we rescale things, we know that it affects everything. And this is going to be 16 times 0.8, which is 12.8. Okay, if we do B, this one's going to be doing rescaling and it's going to have a shift as well. Remember, when we rescale anything, it affects both the mean and the standard deviation. So the multiplying by 2 here is going to have an effect. The 100, so the minus 100, remember that if I shift data, it will not affect my standard deviation. So be careful about this one. So we're going to have 2 times the 120 minus 100 to get my new mean. That's going to be 140. And then we're going to have, in this example, it's just going to be 2 times 12 to give me 24 as my new standard deviation. Remember, the 100, the subtraction, doesn't affect any measure of spread. Okay, now we're going to come to what we have to kind of change our mindset on. X plus 2y. In this case, we are going to be looking at the means. No matter what you're going to be doing, it's going to be all the same kind of thing, right? We're going to have 120 plus 2 times 300, right? So that's going to be 720. Means play well together. Means do exactly what they're supposed to do. They follow the rules. However, standard deviations typically don't always do that. When we combine standard deviations, if you remember from the notes, if you read in the book, we cannot add standard deviations. And so when I'm looking to find the new standard deviation, I'm going to have to find, so let me kind of bring this on, x plus 2y. In order to find the standard deviation of this distribution, I'm going to have to find the standard deviation for x, and I'm going to have to find the standard deviation for 2y. Well, x is easy. We know the standard deviation for x is 12. The standard deviation of 2y, that's rescaling, so 2 times y, is 32. Now, if I wanted to add them together, I would be wrong here. You cannot add standard deviations. You must add variances. If you remember, if I square the standard deviation, I get the variance. So what we do here is we get the variance here, we get the variance here, and then I square it I get the standard deviation, 12, and I square it to get the variance. Here's the standard deviation of 2y. I'm going to square it to get the variance. I can add variances together. That is definitely a thing. And once I get if I were to simply say 12 squared plus 32 squared, that would give me the variance. That would be 1,168, but that's not what I want. We want the actual standard deviation of this distribution. So I'm going to have to take the square root of that number. So the square root of 1,168 is approximately 34.2. Okay, part D. Notice D is very similar to part C. it's 3x minus y. Here again, the means do just what you think they should do. We're going to do 3 times 120 minus 300. Well, this is going to give me a positive 60, right? No big deal. When I go to find the standard deviation, I'm going to have to find the standard deviation of 3x and the standard deviation of y. 3x, that's easy, that's 36, and the standard deviation for y is 16. Okay, here comes something that's not so intuitive. We know we have to square them, but I'm still going to add. Okay, remember this. Standard deviation squared is variance. I'm allowed to add variances, and variances always add. 100% of the time, always add. So if I'm subtracting here, I'm still going to add. This is one of the biggest mistakes people make in this chapter. That minus sign doesn't have any effect when we're doing standard deviation. Okay, so if I do 36 squared plus 16 squared, I'm going to get the square root of that number. That's going to tell me it's approximately 39.4 is my new standard deviation. Part E. Now it says y1, y2. What that really means is just add the y values twice, right? So we're going to get a mean of 600, 300 plus 300. A standard deviation, remember we can't add standard deviation, so we're going to have to find the variance, so 16 squared plus 16 squared. That's going to be equal to 22 point, let's see, 22.6. That's my standard deviation. There's quite a few problems like this. 25, 26, 27, and 28 all work out very similar to this question. This is something that you're definitely going to see on assessments. And so make sure you kind of do. So A and B are kind of the easy versions. C, D, and E are kind of where it gets a little complicated. So make sure you kind of understand that. You got any questions, let me know. Number 37. We're going to talk about how to deal with continuous variables in this question. What we see here is we have two cereal bowls. And it's asking me in question A, how much do we expect the difference to be, right? How much is more is in the cereal, the large cereal bowl? Well, if I were to pour two cereal bowls out, I'll ask you, well, how much more is that? When you would find the values in each one and you would subtract them. I'd like to know the difference. So we're really investigating the expected value, this is part A, of the large bowl minus the small bowl. I'd like to know the differences in the two groups. So if I do this, it makes perfect sense to say, well, the average amount in the large bowl is 2.5 ounces minus the average bowl in the small bowl, which is 1.5 ounces. So I'd say that I would expect an average difference of just 1 ounce. In part B, they want us to find the standard deviation of the same thing. If you remember from the previous question, even though we're subtracting here, we're still going to find the standard deviation by adding the variances. So the large standard deviation is 0.4, so we'll square that, plus the small standard deviation is 0.3. Multiple or add those together, take the square root, you're going to end up with 0.5 as my standard deviation. Okay. In part C, and this is where it gets interesting, if the difference follows a normal model, pause. That means that this is something I'm going to need. I'm going to need a normal model. That also means I'm probably going to be using Normalcdf, right? So Normalcdf really means a lower value, an upper value, a mean, and a standard deviation. Let's change that to mu and sigma, right? If I have these four values, I can do that. And well, guess what? I'm still investigating the L minus S distribution, right? We want to know what is the probability that the small bowl contains more cereal than the large one. So I'm still finding the differences in the two bowls. So I know the center of this distribution because we found it in part A. It's 1.0. I also know the standard deviation in this group, right? It's equal to 0.5. The next part we have to figure out is, what does this mean? The small bowl contains more than the large one. So I would ask you this: when you're looking for differences of things, if those two values, right, we're investigating this number, L minus S, if this were equal to 0, then I would say there's equal amounts in both groups, right? We would say that's equal numbers or equal value in the different bowl sizes. I'd like to know when the small bowl is larger, when the small bowl has more in it, right? If this number here is larger, that would make this difference not equal to 0, but if L minus S, when S is a larger number, would make the difference negative, right? This number is bigger. When you have a larger number here that's negative, that makes the difference become less than 0. So that's what I want to find out on my normal model. So I'm going to come over here. I don't really know where 0 is exactly, but I'm going to put it right here. And it says, what's the probability, what's the percent of the time that I'm going to get an area below 0, where the small bowl happens to have more area in it than the small bowl? By creating this picture we see right here, I've got everything I need in order to plug into this situation. Okay? What we know is that we have a lower value of -1 E99. We have an upper value of 0. That's where my shaded region stops, the right side of it. We know we have a mean of 1 and a standard deviation of 0.5. I can plug all of this in. What I can find out is that the area is equal to 0.02, we'll round it 3 places, 0.0232. About 2.3% of the time, if I pour bowl cereals like this, I'm going to have a small bowl that contains more cereal than a large bowl does. Not often, but enough. Okay, so that's part C. Let's go to part D. Part D kind of changes the scenario again. This is, what would the mean of standard deviation be if we combined the cereal bowls? Like, what would it be if the total amount were added up, right? So we're changing it to L plus S. And so I want to find the expected value of L plus S. Here again, not really complicated, right? We like the means. It's going to be 2.5 plus 1.5. Tells me the mean is going to be 4.0 ounces, or just 4. You don't have to put 0.0. The next part would be the standard deviation of L plus S. And remember earlier I told you the plus versus the minus doesn't really matter. So I'm really going to have the exact same thing as I had before. So I'm not even going to do the math because I've already done it. It's 0.5. So you have a new mean of 4.0 and a standard deviation of 0.5, just like before. Okay, and we are going to go in and we're going to take that to answer question E. If the total follows a normal model, what's the probability that you poured out more than 4.5 ounces of cereal? This one's a lot nicer than part C because it tells us exactly what to do, right? So part E, we're going to go ahead, we're going to draw that normal curve. I know that the center is going to be at 4. It's wanting to know up here at 4.5. What's the chance that my area, my percent, whatever, occurs more than 4.5 ounces, right? So we've already determined the standard deviation is going to be equal to 0.5. So this is really enough for me to go straight to normal CDF. So normal CDF, this is going to be the lower value, or the left side of the curve. The shaded region is 4.5. The upper value is just 1 E99. And then the mean, of course, is going to be 4, and the standard deviation is going to be 0.5. Now, if I'm skipping ahead and you're like, I don't even remember what normal CDF is, we learned how to use normal CDF. This was a very prevalent topic back in chapter 6. And I told you then this was a super important topic. It's back. It's been back a few times, but this time it's going to be around pretty much for the remainder of the year. So get comfortable seeing normal CDF. It's actually quite easy to use. There's a tutorial on Canvas somewhere back in chapter 6. So that's something you need to go check out. Go back and look at it. I'm just going to type this in. Turns out it's going to be 0.159. So just underneath 16% of the time, we would expect the bowls to go above 4.5 ounces. Okay, if we keep on going, last part, we are at part F. This says, well, what if we had the box of cereal, right? So the box of cereal has a mean of 16.3 ounces and a standard deviation of 0.2 ounces. It wants to know if we were to take the box of cereal and pour out these two bowls, then how much would be expected to be left in the box, and of course the standard deviation to go along with it. So we're investigating a new distribution. So the expected value of the box minus the large bowl minus the small bowl. So I'm kind of creating these little formulas that help me to figure out what to do with my numbers. And so here again, I'm going to do 16.3 minus 2.5 minus 1.5. This is going to give me an expected value of 12.3 ounces would be left in the box after I pour out one of each of these bowls. And of course, standard deviation of all this scenario would be like this. Well, the 0.2 squared for the box. Remember, we don't subtract standard deviations, so we're going to go ahead and add the squares of the standard deviations to get my variances. Turns out that this becomes 0.54, I believe. So we ended up typing it in. Be careful when you add these up and get the numbers right. Yes, and you do get 0.54. And that brings us to the conclusion of question 37. Question 37 is a great one, especially when it's talking about how to use Normalcdf to find these values. If you want some extra practice with 37, questions 38 and 42 and 45. These are all great ones to do. 45, I'll tell you, is a fairly challenging question. That's probably the hardest one of all these, but it's a good one to practice. I think 42 is a great question to look at. It asks you to bring together several different things like this. Of course, this is all up to you. It's up to you if you need to practice these or not. Go ahead and give this a shot. This is definitely one of the harder parts. The quiz tomorrow won't really contain any full-on questions like this, especially since we just kind of started going over it today. So I wouldn't worry too much about that for tomorrow, but for the test, absolutely. So if you got a question, bring it up, whether it's in class or just online. Let me know if I can help you.